Hi, so this is the lesson introducing confidence intervals, and we'll do the first confidence interval in this section as well, the z-interval for the mean. So this is the first section of the inferential statistics part of the course, which is what we'll be doing the whole rest of the course. We talked about this at the beginning of the semester, but inferential methods allow us to generalize from a sample to a population. There are two main ways we do this. One is with confidence intervals, which we're doing this week, and the other is with hypothesis testing, which we'll be doing next week. And then hypothesis testing a few more weeks as well. So just a quick review. A statistic is calculated based on a sample, and a parameter is calculated based on the population. X bar is the sample mean, mu is the population mean, S is the sample standard deviation, and sigma is the population standard deviation. If you don't remember those, then you should be making a note card for that and keep those handy. So this is a definition of a point estimate. If we had to guess the value of a parameter, it would be the point estimate. And really the point estimate is just the corresponding statistic to the parameter we're looking for. So the point estimate for mu is X bar, the point estimate for sigma is S. So what happens is if we want to know the population mean, but we don't have access to the entire population, we take a sample. And then we expect that X bar is a good estimate for mu. Okay, and you remember from the central limit theorem, we said that X bar is centered around mu. So this section and the next section, we'll talk about the mean. And then we'll do the proportion later on. So there's a thing called sampling error, which is not a mistake. It's just this natural tendency that when you take a sample, it's not going to be exactly the same. The statistic is not going to be exactly the same as the parameter. There's that natural difference that's going to occur because, you know, if you take a sample, well, I don't know any other way to say it, then it's not going to be quite the same. So that's called sampling error. And so that's why we do a confidence interval. We do a confidence interval, which is an interval that we're pretty sure includes the value of the parameter. How sure are we? Well, we can be any percent sure we decide to be, but the three common ones are 90%, 95%, or 99%. A confidence interval is always of the form point estimate plus or minus some margin of error. And you've probably heard that before when they say during an election, you know, candidate A is winning by 3 percentage points with a margin of error of 5 percentage points, which means it could be 3 plus or minus 5. It could be anywhere 5 points away from 3. So in different settings, we'll have a different point estimate and a different calculation for the margin of error. So the first thing we're going to look at is the z confidence interval for mu. We're going to use this when the population standard deviation is known, which is not really realistic, but we mainly look at it because it connects to the central limit theorem. In real life, nobody ever does the z interval. But once you figure out how to do the z interval, the t interval follows right behind it, which is what people do instead of the z. So let's look at the quantity z alpha over 2. So alpha is the area in the tails of the standard normal distribution. So we saw the quantity z with a subscript before, and this is exactly what this is here. Alpha is going to be 1 minus the confidence level. So for a 90% confidence interval, alpha is going to be 0.1. So again, with the 90% confidence interval, the total area in the tail is 0.1. So that's the tails put together. The tails are symmetric, so we divide by 2, and we get each tail has an area of 0.05. So that means that the area below Z alpha over 2 is 0.95, which is the same as we're looking for Z of 0.05. So if we look up 0.95 in the middle of the table, we get 1.645. And that's going to be a number that we're going to plug in on the calculator. So if we use the same reasoning to try to find Z alpha over 2 for a 95% confidence interval and a 99% confidence interval, give that a try, pause the video, and try that before you continue. Alright, so the answers are 1.96, and actually 2.575 is a little more accurate for a 99% confidence interval. And like I said, these values are going to be inputs into the formula in just a minute. So here's the formula. It looks a little bit scary, but it's not too bad. All you have to do is plug and chug. So it's x bar plus or minus that value of Z that we just talked about times sigma over the square root of n. This formula again assumes that sigma, the population standard deviation, is known. If it's not, then we're going to use the formula in the next section. We don't make too big of a deal about this, but we also need either a large sample size, greater than or equal to 30, or we need to know that we are sampling from a normal distribution. So again, I don't make a big deal out of it with the Z. With the T we will. So here's an example. We've got a random sample of 50 computer programmers, and we get a sample mean of 42,500. We assume we know the population standard deviation, and they want a 95% confidence interval. Again, notice the population standard deviation means we're looking at sigma. So that's why this is a Z. So we plug in x bar is 42,500 plus or minus that value of Z that we found for a 95% confidence interval times sigma, which is 3,100, over the square root of the sample size. So if you plug into the calculator and do, we can get the calculator, 1.96 times, well, I'm having trouble with the calculator. So 1.96 times 3,100 over the square root of 50, that'll give you $859.28. So 42,500 minus 859.28 gives you this amount, and 42,500 plus the margin of error gives you this amount. Okay, so when we put them in parentheses, that's interval notation, and that means this is the interval from $41,640.72 up to $43,359.28. Okay. So interpretation of an interval is very important. My college statistics professor always told us, and this is my philosophy too, you can do a beautiful statistical analysis, very intricate, but if you can't explain to people what it means, then it doesn't matter, nobody cares. So for the confidence interval we just calculated, here are a couple of valid valid interpretations. With 95% confidence, the mean of all, or the mean of the population, is in the interval this value to this value. Or we are 95% confident that the true mean, the population mean, is between these two values. Okay? Either one of those is fine. You do have to be careful though, because there are some invalid interpretations. And by the way, with these two sentences, if you just memorize them, change the values, change the scenario, you'll be fine. You can use the same setup. Okay, so here's some incorrect interpretations. We're 95% confident that the mean salary falls in the interval. I know that's subtle, but falls indicates that mu is a random variable that kind of moves around. I always picture a marble on a roulette wheel when you talk about falls. But mu is a fixed quantity. It doesn't vary. So say instead of falls is contained in or just is in the interval. Second one, we're 95% confident that the mean salary of the sample is in the interval. Well, the problem with that is we know what the sample mean is. So we don't want to infer about that. And there are a lot of different variations of that. We're 95% confident that the mean of the computer programmers, which sounds subtle, but it is implying that we're talking about the sample. So we know what the sample mean is. In fact, it's always going to be right smack in the middle of the confidence interval. So we want to infer about the population mean. So you always should indicate that it's the population mean or the mean of all of the computer programmers, not just the ones in the sample. The third one, 95% of all computer programmers have starting salaries between that. Don't get confused between this and the empirical rule, which did talk about a proportion of the sample or the population. The confidence interval does not give you a proportion of the population. It gives us an interval that we are a certain percentage certain includes mu. Okay? So StatCrunch will calculate some confidence intervals for you. It does the Z intervals. And I want you to know how to do that. However, for the Z interval and the T interval, I think it'll help your understanding if you do some of them by hand. So I want you to be able to do them by hand as well as in StatCrunch. Okay, so watch the video about how to use StatCrunch to do the confidence intervals. I have two more slides here about linking to the central limit theorem. I'm going to let you read those two slides. Because this is an online class and you kind of have a lot to do this week, I don't want to get into this, so I'm just going to let you read those two slides. All right, that's it for Z intervals.